Today we're going to design a content delivery network for a Netflix-like video streaming service. So the main goal of CDN, as most of you already know, is to get content to users as fast as possible, no matter where they are in the world. The big picture here is simple. We have an original cluster, the ultimate source of all our content. Then, we've got this point of presence scattered around the globe. These POPs pull from the main cluster, acting like local cache close to our users. Certain functional requirements should be met. User communication. So obviously we need to handle talking to our users, handling requests and sending data back and forth. Pulling from original cluster. POPs needs to know how to grab content from our main cluster. Content delivery. Then of course we've got to serve the content to the end user from the closest POP. Keeping content fresh. Let's not forget all the POPs need the latest and greatest content always. Timely delivery. Sometimes the internet is slow, we get it. The system needs to be smart enough to adapt like low in video quality when bandwidth is tight. Also let's consider non-functional requirements, like low latency, we are talking about speed rate, minimum lag time is a must. Reliability, the system got to be robust, no one likes downtime or glitchy streams. Scalability, as we grow the system should too, without making our lives a coding nightmare. And that's the rundown. We're aiming to build a CDN that's quick, reliable and can scale with us as we go. Now moving to calculating some metrics. Let's estimate the total number of users at around 200 million. Assuming that 10% of users interact with the platform at the same time, we got 20 million active users. Let's suggest that every active user sends one request every minute. That makes RPS equal around 33,000. This includes general browsing as well as video streaming. For content stores, we focus on videos as they take the most space. Let's assume Netflix has 100,000 hours of content. Also assume that high-quality Full HD video stream might consume about 3 to 5 gigabytes of data per hour. 4K content can be much higher, but not all content is available in 4K. Taking an average of 4 gigabytes per hour, 100,000 hours of content would be 400,000 gigabytes or 400 terabytes. However, Netflix uses adaptive streaming, which means they store multiple versions of each video at different quality levels. If we assume they store an average of 5 versions for each video, low quality to 4K, and considering that we have lower resolution taking less space than our base of Full HD, let's multiply by 4 the previous estimate and get 1,600 terabytes or 1.6 petabytes. Moving on to system design. Firstly, we will explore high-level routing mechanisms that come into play when a user issues a web request. The cornerstone of this operation is a domain name system, or DNS, which serves to resolve human-readable domain names into IP addresses. There are two primary methodologies for IP address allocation and routing, unicast and anycast. Firstly, let's consider unicast routing. In a unicast system, each IP address is mapped to a single server, efficiently enabling one-to-one communication. The primary advantages of unicast include its stability, providing a reliable one-to-one communication channel, and its simplicity in terms of setup and management. However, unicast presents scalability issues, particularly for services that need to disseminate identical data to a large user base. Additionally, there is a potential for increased latency, especially if the server in question is either distant or overwhelmed with requests. On the flip side, we have anycast routing. Anycast allows for one IP address to correspond to multiple servers. The network then routes incoming user requests to the geographically nearest server. Content delivery networks frequently leverage anycast for efficient content delivery, thereby reducing latency and optimizing load distribution. While anycast offers the benefit of reduced latency and enhanced redundancy, it comes with its own set of challenges. These include potential routing instability, particularly for long-lived connections, and the inherent complexity in setup and management. On screen you can see a rough example of unicast and anycast. Our client located in US region requests netflix.com using, for example, his browser or mobile phone, and then a server returns one IP address. In case of unicast, this IP address can only connect you to one server. But in case of anycast, this IP address allows you to connect to many servers. Alright, now let's take a look at high-level architecture of point of presence for content delivery net. So our client's request got to the nearest available POP. When the request arrived, it encounters the IP gateway, a crucial component that performs a multitude of functions beyond just request routing. The IP gateway is responsible for IP composition. That means that for each incoming request, the gateway may need to communicate with multiple backend servers to compile the necessary data for comprehensive client response. The gateway also offers analytics and monitoring capabilities. It tracks IP usage and produces valuable insights into traffic patterns, service utilization, and possible bottlenecks. Additional functions of the IP gateway include request and response transformation, where the gateway may alter data formats or HTTP headers. It also takes on the role of rate limiting, regulating the frequency of requests from each client. The gateway provides a centralized point for error handling, enhancing the system's resilience. Lastly, from the security standpoint, the gateway ensures only authenticated and authorized requests proceed to the backend service. After navigating through the IP gateway, the client's request is sent to the delivery service. This service checks its repositories to determine if the request content is available. If available, the content is then returned to the client via the IP gateway. If the content is not in the delivery service repository, the gateway is informed about it, which then notifies the client. For this inquiry, the delivery service may consult either the metadata database or the storage. Let's talk about what kind of data we can keep in each of them. First, let's discuss metadata database. This database stores information that is crucial for content but doesn't contain the content itself. It holds details such as content titles, durations and content formats, and bit rates. Additionally, metadata database stores location data, indicating where specific chunks or files of content are stored on a particular server. It can also keep track of content popularity metrics useful for implementing cache replacement strategies like LRU or LFU. LRU stands for least recently used, and LFU stands for least frequently used. In terms of specific implementations, metadata database can be realized using distributed databases like Apache Cassandra or Amazon DynamoDB. These systems are designed for high availability, low latency, and seamless scalability, which are all desirable features for a CDN. The use of distributed databases adds a layer of resilience. If one server goes offline, the metadata can still be accessed from another server in the network. Now, let's move on to storage. This is a component where actual content files are physically stored. This could be videos, images, or even text like subtitles. Within the storage, the content is often broken down into files or chunks for more manageable storage and retrieval. Redundancy is built in, with multiple copies of popular content stored in for high availability. For specific implementation of storage, distributed file systems like Google GFS or Amazon S3 are common choices. This system breaks down large files into small chunks and distributes them across multiple nodes. This adds fault tolerance to the storage component, and if a node goes offline and does not contain a redundant copy, can still serve the content. Great, now we have an idea of what data and where our delivery service can get. Now focus on a situation when it has returned with nothing to the gateway. In that kind of circumstances, gateway will route user requests to external servers, which we call communicator. This service can communicate with other points of presence and the regional cluster, which allows it to decide which one of them can possibly fulfill user request. Also, IP Gateway will send requests about missing content to an enrichment service. Depending on our strategy, we can keep track of how many times certain content was missing, and only after several failures send such a request to enrichment service. This service is responsible for getting content and metadata from communicator, filling metadata database and storage with this data. To improve the non-functional aspects of our system, we can include several critical components. First on the list is load balancer, to ensure content is served with high availability and minimal latency. The load balancer will do the heavy lifting of spreading incoming requests across our multiple servers, preventing any single point of failure or bottleneck. And Nginx could serve as a robust software-based solution for this. Features like session persistence and auto-scaling can be integrated, adapting to the varying levels of incoming CDN traffic. Health checks will be in place to route traffic away from any servers that are down or struggling. We'll also want monitoring capabilities for a complete picture of performance metrics and to set alerts for possible issues. To bolster security, the DDoS protection can be layered in. In order to up content delivery speed, a robust cache mechanism is essential. We add one of those to delivery service. This will hold a copy of popular and frequently requested content for immediate delivery. So the cache will also contain metadata to help with smart eviction policies like LRU, least recently used. For ultra-fast data retrieval, and in-memory database like Redis is a strong candidate. We will configure TTL, or time to leave, values to maintain data freshness across various content types. A prefetching strategy can also be implemented to proactively store content that is likely to be in high demand. In addition, cache and validation mechanisms will keep the cache and origin servers in sync. We can also leverage data compression techniques to save on storage and enhance retrieval speed. Now let's talk about content distribution. So, big CDNs often use what we call a tree-style layout. This just means you've got the main server at the top, which is like the root of the tree. This main server holds all the content that needs to go out to the local servers. Then you've got middle-level servers. Think of them like the branches of the tree. They are sort of like pit stops for the content before it gets to the final servers, which we call leaf nodes, or just local servers. These local servers are close to the people using the content, so it gets to them super fast. When something changes at the top server, the whole tree gets updated all the way from the branches to the leaves. Advantage of such a model: efficient bandwidth utilization. By transmitting data down the tree, the network minimizes redundant data transfers, thereby conserving bandwidth. Fault tolerance. The architecture is designed to route data through alternative branches in the event of an intermediate node failure, thus ensuring uninterrupted service. Scalability. The hierarchical nature of design facilitates easy infusion of new nodes at either the intermediate or leaf level, as dictated by increasing demand or geographic expansion. Load balancer. Intermediate nodes possess the capability to manage data traffic efficiently. They can distribute data down different branches based on real-time network conditions such as load or latency. Enhanced security. Multiple layers of security protocols can be implemented at each stage of the distribution process, strengthening the network's defense mechanism against unauthorized access or data breaches. On the screen you can see some depiction of such a system. On the top we have a regional cluster that throws data in some regional clusters, like for example U West or U East, and then to the point of presence. Also we have some intermediary between them, but just for simplicity of picture I put one intermediate layer and then just pop of presence. Strategies for getting our content. CDNs commonly use a blend of push and pull strategies, each with unique advantages and trade-off. So let's unpack these two models. Starting with the push system. Here the content provider takes the initiative to distribute the content to various POPs in the CDN. This distribution occurs as soon as the content is generated or updated at the origin server. The upside includes predictability, content freshness, and reducing the load on the original server. However, this approach can waste bandwidth by pushing infrequently accessed content to all edge servers. It can also add complexity in content management and reduce latency in content updates. On the flip side, the pull system allows edge servers to request content from the original server only when deemed necessary. The benefits here are better bandwidth and storage efficiency, straightforward operation, and suitability for dynamic content. But this model also has downsides, like potential latency in initial requests and possible strain on the original server during traffic spikes. Additionally, risk serving outdated content if the detailed settings aren't configured precisely. Now, when should you choose one over the other? For frequently updated but time-sensitive static content like software updates or daily podcasts, a push model is often preferable. If you're dealing with dynamic or user-specific content, a pull system can be more efficient. Most CDNs actually employ a mix of both strategies, pushing essential content and pulling the less frequently accessed or more dynamic types. Now let's revisit our requirements. Let's start with functional requirements. Handling communication with users. The IP gateway is the first point of contact that handles user requests, routes them through the system, communicating with multiple backend services, transforming data, and ensuring only after twice requests pass through. Treating data from original cluster. Enrichment service handles this part. Also, we have covered tree-like content distribution model and push-pull strategies that help with this aspect. Delivering content to users. The delivery service in each POP ensures that the request content is delivered to the user. If it's not available on the local POP, the request gets rerouted to an external service that can fulfill it. Make sure content is up to date. Both push and pull strategies are used for content distribution. Cache and validation strategies and DTL values are employed to ensure that the content served is fresh and up to date. Ensure timely delivery of content. Anycast routing reduces latency by routing users' requests to geographically nearest POP. The system can also adapt to low bandwidth conditions by lowering the quality of content as per the adaptive streaming strategy. Now to non-functional requirements. Low latency. The use of Anycast routing, local POPs, and a strong caching mechanism ensures low latency. The tree-style distribution model allowed balancing further optimize latency. Reliability. Redundancies are built in the system. High availability ensures through distributed databases for metadata and distributed file system for actual content. Load balancer route traffic away from failing servers. Scalability. The tree-style distribution model and the use of distributed databases and file systems are inherently scalable. The design system is capable of handling our estimation of 33,000 RPS and 1.6 petabytes of data stored and covering future growth. Thank you for being with me. Goodbye.